Welcome back. We now present the fundamental theorem of cyclic groups, and there are three statements in this theorem. The first two follows almost immediately from the previous results that we have seen. The third one needs a little bit more work, but it's not difficult. But I'm going to skip the proof of this theorem. So the first statement is that every subgroup of a cyclic group is cyclic. So recall that we have proved this theorem in the case of the set of integers. If the order of the subgroup generated by A is n, well, that means that's also the order of the element A. Then the order of any subgroup of the group generated by A divides n. In other words, the order of a finite cyclic group is divisible by the order of any of its subgroups. So again, we are assuming that G is a cyclic group generated by A and order of A is n, and that is the order of G is also n, and we are saying that the order of any subgroup of G divides the order of the group G. So put simply, the order of a finite cyclic group is divisible by the order of any of its subgroups. If the order of A is n, then for each positive integer k, for each positive divisor k of n, the group generated by A has exactly one subgroup of order k, namely the subgroup generated by A to the power n over k. So consider the group generated by A, right? You have a cyclic group generated by A, and n is the order of A. Then for each divisor k of n, this subgroup has exactly one. This cyclic group has exactly one subgroup of order k, which is generated by A to the power n over k. Okay, so you need to make sure that you read each of these statements and make sure that you understand what they are telling us. If we apply number 3 to Zn, the set of integers mod n, then we get the following result. That so consider the group Zn, which is a cyclic group generated by 1, and then for any divisor k of n, Zn has exactly one subgroup of order k, which is generated by n over k times 1, which is simply n over k. These are the only subgroups of Zn. So once again, the third part of the fundamental theorem of cyclic groups, when applied to Zn, where we are using the additive notation. So you have to understand that you have to understand that when we are stating this theorem, we are always using multiplicative notation, but you can always state these theorems in the additive notation. So in the additive notation, instead of writing A to the n over k, we would be writing n over k times A. And so instead of powers of A, you're looking at multiples of A. So when we apply that to Zn, then this is what we get. So we can find all subgroups of Zn by applying this corollary. Okay, so let's do an example and apply this apply the third statement here, which is basically the corollary here. So we want to list out all the subgroups of Z30. All right, so I'm going to make a table basically. So in the first column, I'm writing all the different divisors of 30. So what are the divisors of 30? Well, 30 itself is a divisor of 30. Next biggest divisor would be 15. The next biggest would be 10, 6, 5, 3, 2, 1. These are all the divisors of 30, where 30 is the order of this cyclic group. Recall that this cyclic group is an additive group. It is generated by 1. So here we know that for each divisor k of the order of the cyclic group, it has exactly one subgroup of order k generated by n over k, right? So we have this subgroup of order 30 generated by 30 divided by 30. So here n is 30. N is the order of the cyclic group, and k is the divisor here. So the subgroup of order 30 is generated by 1, which of course makes sense. This is simply Z30 itself. So Z30 itself is a subgroup Z30 is a subgroup of itself. The divisor 15, so we have a subgroup of order 15, which is generated by 30 divided by 15, which is 2. So 2 generates the subgroup of order 30. The subgroup of order 10, that's generated by 30 divided by 10, which is 3. And the subgroup of order 6 is generated by 30 over 6, which is 5, and so on. So we have that for each divisor of 30, we have exactly one subgroup of order equal to that divisor, and we know what it is generated by. It is generated by the order of the group divided by the divisor. I'm going to make a subgroup tower here with this subgroups. So here I made a subgroup tower, a tower for the subgroups of Z30. So these are all the subgroups, and then the arrow indicates that the one below is a subgroup of the one above. So obviously the subgroup generated by 0 is the subgroup generated by 0 means it only has 0 in it. So that is a subgroup of each of the other subgroups. And so 6 is the subgroup generated by 6 is a subgroup of the subgroup generated by 2, because 6 is a multiple of 2. And then similarly 15 is a multiple of 5. So the subgroup generated by 15 is going to be a subgroup of the subgroup generated by 5, and so on. So the arrows indicate that the one below is a subgroup of the ones above it. So if you follow the arrows, this is a subgroup of this, and this. This is a subgroup of this and this, and this, and so on. All right, so sometimes creating a tower of the subgroups gives us the structure of the subgroups of a group. Let's say now that I want to find the generators of the subgroup of order 9 in Z36. So Z36 has exactly one subgroup of order 9, and we want to find all the generators of that subgroup. So Z36 has exactly one subgroup, namely the subgroup generated by 36 divided by 9 which is 4. So the subgroup generated by 4 is the subgroup of order 9, and this is by applying the fundamental theorem of cyclic groups and directly using the corollary that followed it. The other generators, so we are now focusing on this subgroup generated by 4, which has order 9. The other generators of this group, of this subgroup, would be of the form k times 4, where k is relatively prime to 9. Now, if I had multiplicative notation, then I would have said the other generators are of the form 4 to the power k, where k is relatively prime to the order of this guy, which is 9. So the other generators will be k times 4, where k is relatively prime to 9. So what are they then? Well, k could be 1, k could be 2, then I get 8. K couldn't be 3 because that's not relatively prime to 9. 4, k could be 4, then I get 16. K could be 5, then I get 20. K could be 7, then I get it 28, and k could be 8. That's going to give me 32. And these are all the generators of this subgroup here. So in other words, the subgroup generated by 4 is the same as the subgroup generated by 2 times 4, which is equal to the subgroup generated by 4 times 4, and so on. So again, let me remind you which result am I using here. So this is the result that I'm using, that the subgroup generated by a to the k is the same as the subgroup generated by a, if and only if k is relatively prime to the order of a. And think about using this in the additive notation. Then we would be applying it in this way. Okay, so I'll stop the video here. In the next video, we will be looking at Lagrange's theorem.